Hendrik Ulbricht from the University of Southampton.
Thanks for the introduction. Thanks for having me. Good to be here. Good to see you. Thanks to the organizers for running the show. So I wanted to talk about also experiments. So like Peter, I'm an experimentalist and I also work with levitated systems. And I wanted to, in a way, also give an overview of where we actually are in using these systems to test quantum mechanics and gravity, maybe not in one single experiment, but you know, in the same type of experiment with the intention to then bring them together at some point. So I have to, you know, check the technology. I wanted first thank people. So you know, feel free, please, to interrupt me and ask questions. So it's, you know, there is some structure to the talk, but you know, happy to deviate and to discuss things. So there's like a list of people I wanted to thank, mostly the group in Southampton, and one of them is Rafael, who sits there, and now he's back here in Brazil, but he spent like a year with us, and I will talk about the experiments which we did together, and that's ongoing stuff. So so here's the plan for today. I will talk about experiments which test quantum mechanics in the macroscopic domain, so how to push the mass up in, if you want, quantum superpositions. And then the second is to talk about gravity experiments and how to actually push mass down in these experiments. So by that I mean the source mass. So you maybe know that in gravity experiments you typically have two masses. One is called the source mass, that's the one which generates gravity, and then there's a second mass which is used to probe the gravity which is generated by the first. Of course, if you know from, you know, what we know from physics is that that can be swapped, and you know, there's actually not this order, but in a way it's good for an experimentalist to know actually what is the function of which part of the experiment. So, and there's a source mass, and that has to be like really small. That's the regime we want to probe. Before I go to this, actually I don't have it today. So this is like the mass scale, and I thought there's this piano. It's actually quite nice. I can try, let me see. Okay, so this is a mass scale, and this is very simple, right? So you can forget everything which is written there. This is just some ideas of, you know, models and predictions where gravity is affecting a quantum system. The only thing you have to take from this slide is there's like small mass, and that's the domain of quantum mechanics. So I would say that's here. Quantum mechanics. I cannot speak that high. And then here, that is like the large mass stuff. So that is where gravity is, right? So gravity here. Gravity. So, yeah. And now what we want to do in experiments is we actually want to go down gravity. Yeah. And quantum mechanics, the opposite. And then at some point, the two meet somewhere here, maybe. I don't know. So I will talk about experiments and where they actually are on this graph. I will come back to this. This is like my guiding figure of merit, if you want. So it's in simplification. So we know for quantum systems is not only the mass. There are like other parameters which are important, like for instance the size of the superposition. But for simplicity and just for the sake of this talk, I just reduce it to, you know, a mass. Okay, so I go to the next slide. That was like all the music, unfortunately, in this presentation. We can maybe have a jam session later, but I should concentrate on physics. Okay, so levitated mechanical systems. I talk about, you know, generating superpositions and how to do it. There's, of course, like the classic way of doing it is shown here on the left-hand side. If this thing works, here's the red dot. So left-hand side is like an interferometer, matter wave interferometer. You have a massive particle, you put it in a trap, you prepare an initial state, which is, you know, done by cooling. So you could say you prepare spatial coherence. And then you turn the trap off. So here you have like an harmonic oscillator, a trapped system. It goes back and forth. And then when you turn off the trap, it becomes a freely moving particle, yeah, so free evolution. And at some point, which is determined by quantum mechanics, again I find it here, so there's a beam splitter, it could be a grating or a Stern-Gerlach beam splitter, whatever you want. Yeah? So that is dividing the wavefront, and then again, yet another time step later, you have here a detection system where you look at the overlap between the two partial waves which you generated at your beam splitter. Yeah? So that is like a, Mach-10er interferometer or double slit diffraction experiment. So it just, very schematic in that sense. So if you think about it, you can actually do a proper simulation, which we have done here using fancy Wigner function. That's like 10 years ago. You can basically predict at what conditions for a particle of a given mass, in this case it's like 1 million or 10 million atomic mass units, you can see a quantum interference fringe, an interference pattern at your detection system. And when you think about this experiment, what is actually the really limiting factor, if you want to now push the mass up and up, is the time it takes from here, from your source to the detector. That is this free evolution time. So you have the free propagation of the particle, and during this free propagation, the wave function spreads. And now that takes some time. So if it's like the natural expansion, then this is given by a 1/m term in the Schrödinger equation. So, and if you have a large mass, then it takes really long, right? And the problem with this is that if you do this on Earth, that your experiment is limited by this. Things fall. I hope it doesn't, it's not broke. So, you're limited in time, So I will now talk about experiments. So that's a graph which shows this more, directly. So here's the Talbot time. So the Talbot time is in this, that's a Talbot interferometer. It's basically using near field wave, things to simulate this. And there's a certain distance, Talbot distance, or if it's a time for the particle to drop, then it's a Talbot time, and that is nothing else than saying there's this natural spread of the wave function which takes time. So that is reflected as a Talbot time here, and you see if you want to have a Talbot time of some seconds or so, which you need for 10 to the 8 atomic mass units, so 100 million atomic mass units, so that is 10 to the minus 21 kilograms, then you're limited already by your free fall time on Earth if you want to not build a 100-meter long experiment where you have sufficient drop time. So this is maybe something where you have to go into space, and I will talk about the space stuff. So so I will look into options, how to optimize, how to maximize, how to extend this free evolution time in these experiments. For this, let me introduce the experiments we're doing. It's also optical levitation, so a laser is focused. We use parabolic mirrors to a diffraction limited spot. We use 1550 nanometer light, so telecoms wavelengths. We trap 100 nanometer silica particles, so glass beads, in the focal point, and we use the very same laser light in Rayleigh scattering and back reflection or backscattering to detect the motion of the particle, and by doing this we can actually detect the motion of the particle in XYZ, and if the particle is non-spherical, as we have seen beautifully in Peter's talk, then also in this very simple setup you can also see rotational features. So you detect this by a simple photodiode. So here's a setup, there's your laser, it goes into the trap, the particle would be trapped here. The backscattered light is refocused or recollimated is a better word by this parabola, and then it goes into the photodiode. It's a very simple photodetector which detects the time domain signal. So you basically measure the position, which is a sinusoidal function versus time, and then you can use, for instance, lock-in amplifiers or other electronics to act on the light which goes in the trap, then that you can use for feedback control, so you can cool the motion, and that's shown on the right-hand side. So you see now if I take this time domain data and I do something like a Fourier transform, I get the power spectral density, so I get these peaks which belong to all the motional features in the system. So that would be, that's like a power spectral density on the right-hand side, which gives you the Z motion and the X and the Y motion. And then I can turn on my cooling loop, my feedback loop, and I can cool the center of mass motion to, almost to the noise floor. So these blue bits here are basically the remaining parts of these peaks, and then I integrate over the area of these peaks, and that's the temperature or the kinetic energy in that specific mode of mechanical motion. Okay, so that's our basic system, and that is what I would put like at the starting point. You remember the Talbot interferometer, that would be like the trap part where it starts, where I condition basically my harmonic oscillator system, and I do exactly this kind of cooling. I cool to something like a millikelvin, and it's sufficient for preparing spatial coherence to do an interferometer scheme. Okay, next one. So now, so long free coherent evolution time, how can I get this? So if I go and I say, okay, I turn off my trap, yeah, that's the easiest thing I can do. I need free evolution, and I have my particle in a trap, and the trap has, I don't know, the size of a micrometer, and I turn it off, and then the particle starts to fall, and I don't have anything else, so I have to recapture my particle in the same trap. So then I have something like, if I remember the number correctly, so something like some 100 microseconds, yeah, to recapture. So I have the particle trapped here, I turn off the trap, and then I turn it on again, 500 microseconds, and in this time the particle falls, and then I can recapture and measure the position again by looking at the oscillation. Yeah, so that is a protocol, and I could easily do, not easily, but I could do interferometry with this. But I would only have a free evolution time of 500 microseconds, which is not enough for like these macroscopic things we want to do. Okay, so now what else can I do? I can do what we call throw and catch. Yeah, so you can basically trap. So this is now here on the right-hand side in this illustration. So you have, again, here's the parabola, here's the particle, which is now slightly off-centric from the trap. It's just for illustration of the free flight trajectory. So you have the particle here, you have a second laser from the bottom, which is kicking. Then the particle goes up, it has a turning point, and somewhere there you overlap with the grating. You apply this beam splitter function, then it comes back and you recapture, and then you can extend this to something like 100 milliseconds. So you gain something like an order of magnitude, or at least a factor of 5, yeah, in your free evolution time. So this is very complicated. We are working on it. We are struggling at the moment with the point that if you kick this with the laser, then the particle is not just going this trajectory, it easily goes in all sorts of directions, and that depends on how good you can cool in X and Y motion, and that depends on how nice the spatial profile of your kicking laser is, and all these kind of things. So, okay, I maybe should say that we're experimentalists. We are, patient to some extent, but we're not super patient. So we always look for things where we can, achieve something faster and easier. So here's like a scheme or an idea for how to extend free evolution times to something like 100 seconds. And that's on a satellite. So there's like a 10-year program which is called MACRO with a large consortium. And the idea of MACRO is to have like a big, let's say, dedicated satellite which goes to a very quiet place, a Lagrange point in the planet system. And then it would sit there, and then you do your protocol. And because you are on a free-falling trajectory or on a zero gravity point in this kind of gravity mapping, in the planetary system, you have like the situation that your particle is basically falling together with your setup. So in principle, you have infinite long free evolution time because you're always, following your particle. That's only true modulus, technical noises. There's of course acceleration in these kind of satellites, which means that effectively the particle relative to your detection system is moving out in a kind of Brownian motion from the center, and that is what limits it to this like 100 seconds or so. Okay, so but here would be like a protocol. That is what I mentioned. So you have like your initial trap, you turn off, the particle remains at again, modulo technical acceleration noise, particle would stay there, then you overlap this. In this case, it's like a cavity which generates a standing light field, which is like the grating. You generate the superposition, and then you turn this off, and you probe basically how, the matter wave has basically formed after this beam splitter operation. So, okay, so that was, all nice, and we wrote together with this consortium a lot of theory papers, and Sanno was involved in this, and we thought, okay, we should do something more concrete, and that was then this one, which is called Op2Space. So that's now a real space project where we have, together with the European Space Agency, the opportunity to fly this box here. So that's like the size of a toaster. So that is 20 centimeters by 20 centimeters by 14 centimeters. And inside the box is an optical trap and a magnetic trap. And the plan is to, fly this, and as a first step show that this levitated technology actually works in orbit. Yeah? And the thing which we haven't achieved yet and which we want to demonstrate is to load the particle in an optical trap from a piezo source. If you look inside the box, just to bore you a little bit with some technical details, so it's a fully autonomous system. So there's an electronics board. I think there are more slides here. So there is like an electronics board, which is here on the right-hand side, which has a laser driver. So that's our 1550 diode laser. That's on a control board, which is stabilizing the laser. There's also a photodetector, which is on the backside, which you don't see, which is the photodiode. And then there's an FPGA, which is basically operating these different components and is running everything. And there's a microcontroller, which is saving data. So that is basically just upon a trigger from the satellite, the whole procedure starts and runs a protocol to load the particle, trap a particle, and then detect the motion. And here are vacuum chambers. So this is like a, 10 centimeter long stainless steel vacuum chamber. Here's an optical trap, and here's this diamagnetic trap, and we, will then in orbit basically use these and take data from there. So again, not in this very first mission, but like in a maybe 5 years horizon with more opportunities of that kind, one can imagine to do this kind of superposition experiment, the interferometry on a satellite, with the benefit of having, let's say, these 100 seconds of free evolution time. Yeah. Okay. Again, I remind you, we're not really patient people. So while we're working on this and try to basically help the quantum system to have sufficiently long time to evolve freely, we also think about how can we actually engineer the system and can somehow accelerate the evolution. Yeah? Maybe we can spread basically the wave function faster than it is dictated by the Schrödinger, evolution. And that's possible. So in atoms, people do this, of course. And Gavin talked about the this Stern-Gerlach, interferometry scheme. And if you have a Stern-Gerlach beam splitter, that is basically by having this external magnetic field gradient, which is acting on your spin superposition state. I have to keep the microphone close to my mouth. And then you have the external magnetic field. Then basically the magnetic force is pulling basically the two parts of the superposition apart from each other with super high speed. And that is like an inflation or expansion operation. And because we don't work with these kind of magnetic systems, so we thought, how can we do this in optics? And the answer is this here, not the only one, but a possible one, is to modulate the optical trap by a so-called frequency jump operation. So what you do is you have like the optical trap, and I can maybe try to explain it here. So you have initially the particle in your trap, it's oscillating, and then at a certain time you basically reduce the frequency of your trap, and you do this by reducing the light intensity which you send to the trap. Yeah? So you make your trap, now I have to move my microphone again for my mouth. So you go to a shallow trap, then after 1/4 of an oscillation period, you switch back to a deep trap. So, and if you do this, then you can basically see the following thing that's now here on the bottom of this slide. So you start initially with, that's an experimental circle, or a spherical distribution. So a thermal state, which is, I have to say, not the minimum uncertainty state. So calling it squeezing is pushing it a little bit. It's what is typically called in quantum optics quashing. So you have a thermal state, and you do an operation which is affecting the shape of the state by not changing the energy of the state. Yeah? So here is what happens after the pulse. So you see the initially almost, circular distribution turns into like an elliptic one, so like a typical for squeezing. And now this thing, because it's an harmonic oscillator, is rotating in phase space, and by interaction with background gas in a vacuum chamber, so we have still some collisions there, it's rethermalizing into a thermal state, and that is basically what determines the decay here. Yeah? So here in this point we do the operation of the frequency jump, and then that gives like a large amplitude oscillation, and that rings down, and the time constant of the ring down is matching basically the gas collision dynamics. So how am I on time? It's like still like a lot of time, or? Okay, cool. So, okay, so now that is very good. But I said, okay, what we want to do is we want to basically engineer the state, yeah? And the good way to look at the state is in phase space. And now it's nice if you can make a squeeze state, but it would be even nicer to do like a superposition. So how can you do something which is like a superposition? And the answer is this here. Again, not the only one, but the possible one. So you can actually repeat the operation of this frequency jump many times, and you do it in a synchronized way. So you always act at the system when your cigar is orientated in the right position in phase space, and then you do the switch again. So you see here a sequence of pulses. So that's actually the work by Raphael. So he did the simulation of it, and also for this one the experiments. So you start again with your initial thermal state. So this time we managed to do like a really circular one, and then you do one pulse, which is like a extended state, and then you do another one, which is longer, and then you see already that something non-trivial is going on. So you see that actually it's not becoming a long cigar, but it's like curving, and it's looking like a spiral galaxy. And then, what's the reason for this? The reason is that you basically push your state in your trap into a regime where you get effects of nonlinearities, right? So if you have a harmonic trap, it becomes unharmonic if you are on the edge, if you're far away from the center. And what this means is that if your state, or if your particle population is experiencing these nonlinearities, then it travels with a different speed. So in this phase space picture, it means that you get these kind of spirals, and if you just stay brave, and you just you're a good soldier, you just continue with your procedure, and you do more and more squeezing pulses, then what then happens is that these spirals basically come back, and they form this kind of bimodal distribution. Yeah? So now what you have done is you have started with a Gaussian state, a classical Gaussian state, and by pushing the state into these wings to overlap with the nonlinearities, the intrinsic nonlinearities in the trap, you have formed a non-Gaussian state. So this is like a non-Gaussian state. So what I'm saying, if now there's one condition which is missing, and that would be to have coherence here at this state. Yeah? So by cooling, you can again put in coherence into your system, and then what you would see here is basically a state which has this bimodal distribution with some interference pattern and negativity in the middle. So that would be this famous Wigner function of a superposition state. And so we try to do that here. So you see there's a protocol where we now, in addition to squeezing and benefiting from the nonlinear part of the potential, we also do cooling. So we use linear cooling or parametric feedback cooling, and this is experimental data which were taken by Tiberius, and again Raphael did the simulations and basically the mastermind of these experiments. So you see that here you start with a thermal distribution, and then you cool, which means that you reduce the size of your blob in phase space, and then at some point you turn on the squeezing pulses, and then again you get these spirals, and then you get nice bimodal states. But so far no negativities, because we couldn't cool low enough to get this. So this is a simulation here where you would expect, and this is now one of these kind of spiral states where already at this phase you would basically expect to see some negativity. So these are like the yellow parts here as some wiggles on these states in the evolution. Yeah? So we are still working on it, but this would be a protocol which would give you an accelerated evolution of the wave function, and that would help, I think, to generate these superposition states on realistic timescale. So it's likely not the most macroscopic one, so you would have fairly small superposition sizes, but maybe that's also not true. There was this interesting side effect which Raphael discovered in the data, so it's unfortunately not shown too nicely. So there's actually a graph here which shows oscillation, but the important thing is that within 1 millisecond, so you see here these 4 dots, which are 4 representations of the state in phase space when we do the squeezing protocol with also the cooling on. So the initial state is like a pretty small state. So you see this is 0.5 nanometers, so that's like pretty small. So there is already some coherence we claim in this state, and now what we do in 1 millisecond, we basically boost the state. So that's a squeezing factor of something like 24 dB. That's quite big. Yeah. So what we now do is we basically expand the state in 1 millisecond to plus minus hundreds of nanometers. Yeah. So that means what we have done is we have taken, if you want, in a simplified language, is not entirely correct to say it like this, but we take the wave function of this particle, which is like super small because we cool it, yeah, and we get into this regime where it is really like a quantum feature, and then we use this expansion operation to make this quantum state, this wave function, larger than the size of the particle itself. And that's super cool because now we can, for instance, also use this as a precursor to then overlap it here with the beam splitter, because one of the tricky bits is that if you want to split a wave function, you need something which has a higher or a smaller size than the wave function, right? So if you only have 0.5 nanometer, you need something which is only some angstroms to split and say that goes right and that goes left, right? If you have something which is hundreds of nanometers, that's easy. Yeah? You can even use light. Yeah? Okay, so that was quite exciting, and that again is work in progress. And so again, maybe the slightly depressing message is there's no superposition yet, yeah? But we think we are on a good way to get it very soon. I think the next is to go back to our famous map, yeah? And now I have here a marker which basically is where we want to push this, so that's like a realistic goal to go somewhere here, yeah? So this is like molecules, Markus Arndt, now they're like, somewhere up here with what he told us today, that they have 1 million atomic mass units in the sodium clusters. So now with these nanoparticles, we maybe push the mass, slightly higher into this regime. Now I will talk about gravity experiments, and then we go back to the map and see where the gravity experiments bring us at this point. Okay, so 2-mass gravity, I mentioned it already. Here's again like a summary slide to remind us how we actually measure gravity. Here's Cavendish experiment. Here's a torsion pendulum like Eric Adelberger's group is doing. So you have 2 masses to some extent. So here you would have these pair of masses, and then you have the smaller masses, and one is generating gravity and the other one is basically monitoring it or probing it. And you can also do this with atom interferometers. So you have then typically like an external mass of some kilograms where you imprint like a cow face, like in the famous neutron interferometry experiment, which is a probe of the external gravity, and then you can move these mass blocks back and forth. You can maybe use atomic clocks and LIGO and all of this, so these fancy systems. But now you can also use levitated mechanics, and I will show you how. Here's the system. So it's a levitated mechanical system, a magnetic one, so different from the one we are using for pushing for these large mass superposition states. And the way it works, like in a very sketchy way, is that you have a ferromagnet, a permanent magnet sitting here that has a magnetic moment, a permanent magnetic moment, and now you put this in a lead box, you cool the lead box below its critical temperature, it becomes a type 1 superconductor. So what you then have is like an image moment, magnetic moment in here, and that the interaction between the magnetic moment and the image magnetic dipole is giving you a lift force, and then gravity is also acting here to push it down a little, but that So the gravity which is pushing it down and the lift force of this diamagnetic Meissner levitation is actually defining where this particle sits. And then you have, again, XYZ translation motion, and because this has an, it's like a vector, it has this magnetic moment, magnetic dipole moment. There's also rotations alpha, beta, gamma, so you have 6 degrees of freedom. And what we do is then we have a SQUID, superconducting quantum interference device, which is very well known in magnetometry and low temperature physics. There's a little antenna which is pretty close to the magnet. And now if the magnet is moving, then it's inducing like a current. So the magnetic field of this magnet here is inducing a current in this loop, which is then inductively coupled to the SQUID, and you can measure this very, very small current by the SQUID. So that's how we detect position and also rotation. And we can do this with particles as small as some 10 micrometers in radius. So these are neodymium magnets, the same kind of super strong magnets which you know from your fridge, and they look like this, nice and spherical. So okay, so this is like the system which we want to use to probe gravity. Just maybe here to give you some more details. So this is like a typical spectrum which you see, and I have indicated here X, Y, Z, and alpha and beta modes of rotation, and we can also feedback cool basically the center of mass motion and also the rotation by acting mechanically with the piezo. So basically in the same way we do optical cooling by modulating the laser intensity which goes in the optical trap. What we do here is we mechanically kick basically a little bit the particle when it is in a certain phase of its oscillation. Yes, so this is like a spectrum, and then for gravity you would pick basically the strongest mode or the one which you feel is like the best one, and then you can do with this mode a force noise measurement. So let me introduce this concept. So you basically want to measure a force, and the model system is your harmonic oscillator, a mass which is connected to a spring. It's oscillating, and now the oscillation is affected by external forces and also by thermal forces. So you want to measure the external force, but you have a limit which comes from this thermal force, and the thermal force is written down in this type of equation. So you have a thermal bars at the temperature T, and then m is the mass of your oscillator of this guy, omega 0 is the frequency of this oscillator, and q is the quality factor of the oscillation. And if you put in numbers, then this gives you a minimum force which you can measure. Yeah? So now if you can tune these parameters, if you can make the temperature small, the mass small, the frequency small, and the quality factor large, then you can measure pretty small forces. Yeah? And that's what we use for gravity. You can also use it for other things. So there's interesting noises in the universe, and there are discussions with also how that has an effect on quantum mechanics, but I don't talk about this today. So let me just move on and show you the gravity experiment. So that's here. So it's with this levitated particle, which is here in a big cryostat. So there's a picture of the cryostat. I should say this experiment was done with Tjerk Oosterkamp in Leiden. They have a fantastic suite of low temperature experiments also with these vibration isolation systems, which are tuned to basically decouple a specific mechanical mode of your probe from the environment. So this is the cryostat, that's how it looks like, and here's this mass spring system with the levitated particle somewhere here. So that looks in a cartoon sketch like this. There's a zoom in here, so you have in this case we designed basically a specific Tjerk always calls it the levitated the Zeppelin, yeah. So by Led Zeppelin, so that's his pun. It's made of lead. So there's like basically 3 of these particles which are permanent magnets, and there's like a glass sphere glued to it, and that makes that there's like a preferential mode, which is like a torsion, like pendulum mode, which we then use to couple to gravity. So that is all inside here. This is at 10 millikelvin in a dilution refrigerator, and then there are thermal shields, and outside in about 1 meter distance or so, there is like a big bicycle wheel which has 3 masses of 3.4 or so kilograms, and that's rotating so that the mass modulation, so you have like a big mass close to it or a small mass close to it, so that this oscillation is close to the frequency of that mode. Yeah, so you basically resonantly enhance the gravity coupling. And of course, you have to make sure that vibrations of the wheel in particular don't couple basically to, the probe system, and they don't, couple in other ways, only by gravity. And then you measure gravity, which is shown here. So these crosses are the measurement points with error bars for different distances. Yeah, so we basically modified or changed the distance between the Mars wheel and the probe system. And then you see that, it's nicely following like an 1/r or 1/r square law, like expected from, Newtonian gravity. But you see that actually if you plot Newtonian gravity here, then this is where it would be expected with some, allowed margin for deviation. So we have, we can safely say we are outside of the expected range of, Newtonian gravity. So we are measuring less gravity than expected. And now, of course, we could start like a big story and say, hey, we see deviation from Newtonian gravity. But that is like the pitfall for experimentalists, right? So don't be too fast. There are for sure like 10 reasons why this happens in your experiment. And we think actually there's a very good reason, which is in this experiment, and that is that when we turn basically the Mars wheel in this configuration, then gravity is not only affecting this little particle here, but is actually shaking the whole cup. That is basically hung on this Mars spring filter, which has like a, is very, very soft, so that is oscillating at a low frequency. So it's very easy for this Mars wheel to excite basically a motion of this whole thing. And that would have an effect if you model it, which is exactly this kind of reduction. So Tiag is now redesigning this experiment. So there's a, relatively simple idea how to do it. So you have to basically bring the center of mass of this Mars spring system way up. So you have to couple it to like a large block, which sits somewhere here. So then, this oscillation here or this modulation of mass will not affect this. But the really big step we want to do, and that is in preparation in Southampton, is to actually take this source mass system and put it also inside the fridge and be as close as 1 centimeter, 5 minutes, yeah? And then, measure gravity of this, and we are hopeful that this works. And I think the next slide is again that is actually how we want to do it. I don't bore you with details, but this is like a system which we are building at the moment. So I hope we have like the first data before Christmas. That's always, the hope. And then it takes, I don't know why, but it always takes longer. But this is where we think we can go, let's say in the next 2 years. Huh? So, big mass, and then it goes to something like, this is Planck mass. If you expect something special there or not, let's not discuss this, but this is just, micrograms, tens of micrograms. And if you remember, that's maybe like the take-home message that, the quantum system was somewhere here. So that is still like good 10 orders of magnitude, which we have to bridge to really do this experiment where we have at the same time the system in the quantum superposition. And I have not mentioned it, but I'm a bit snobby in my definition of what the superposition state is. So I really want something where the superposition size is larger than the actual size of the object. Yeah? Not something which is like on a femtometer scale or 0-point motion scale. I really want to have like a significant superposition. So if I want to have this, then we still have like 10 orders of magnitude to go. And I'm very optimistic, so it's only 10 orders of magnitude. Hey, come on. So good, so I have like, that's like discussion time and question time already? Okay, so I maybe just a very brief flash. There's this effect which now for something completely different, or maybe not, which is using actually mechanical rotational energy to increase the energy of an electromagnetic wave. So that was predicted by Zeldovich in '71, and it looks a bit like this. So you have a metal cylinder which is rotating at big omega, and then you have an angular momentum mode of light. It can be orbital angular momentum or spin angular momentum. So basically your light has some sort of twisting mode. And if you fulfill this condition here, so if your frequency in the electromagnetic field or electromagnetic wave is smaller than the frequency of the mechanical rotation, which is like a tricky regime, because with light you would need to spin this at, I don't know, 10 to the 14 hertz. Yeah, so that is like super fast, and that's why no one has measured this. So we had this idea. That was actually my how you say, my meditation during COVID was to build this setup. So just, you know, do something, you know, step by step. And then, so what we have found is that if you do like an LC circuit, so here you have a magnetic coil which is connected to a capacitor, which is not shown, and you can basically generate an electromagnetic field at 100 hertz, and you couple it into this ferrite block, which is a blue block, then you transfer basically a magnetic field to overlap with the rotating cylinder. So here's the setup. Here's, you know, the magnetic coil. There are funny stories how that was made. I don't have time to talk about it. And here's like the rotating thing. So now this is 100 hertz and this is 150 hertz. And if you do this, then you see amplification. There's some details of discussion, but basically here you see the amplitude of the electromagnetic field, and the gray one is basically with no rotation, with no you know, rotating metal cylinder. And if we turn on the rotation, depending on the frequency, we basically can amplify the amplitude. Yeah? So that is how you see an amplification of a wave is if the amplitude gets larger. Yeah? So that is shown in this like 1D version. And maybe the very last slide is this here. So we have done a 3D version, which is like with a three-phase configuration. And you see we have botched an electromotor from some company, and have just put in our metal cylinder, aluminum cylinder, to rotate it. And with this you can push this stuff in a regime where you get massive amplification. You actually get generation. Yeah, so you get like super large amplitude. So actually you can, if you're not careful, you can blow the capacitor in your setup. It's such a massive acceleration, and it's actually not amplification anymore, it's generation. So you don't even need an input signal, you just amplify noise. Yeah. So I think that is like super cool. It maybe has a lot of applications also. It's not dissimilar from you know, turbines, and I think people are not aware that there is a regime in which you can push it to get like huge amplifications. But what is really interesting, and that's really the final thing, Thiago, sorry for pushing this, is, so here's for comparison actually what we had with the 1D case, right? So that is like, in comparison, this is like a much larger. So there's a gravity analog where this is called the black hole bomb. So Roger Penrose had the idea that you could pick up super radiance effect, you could pick up rotational energy from a black hole, and you could use it as an energy source. And then there's a runaway solution, then you get this black hole bomb, and this is like the electromagnetic version, we think. But the thing I want to conclude with is this one here. So we want to go into the quantum regime with this, and it's relatively clear how to do this with an electromagnetic wave. So what you have to do is you have to generate basically something electromagnetic which has a vacuum state. So I guess you would use a superconducting LC circuit, so a superconducting circuit. And then you would couple basically the vacuum state of that circuit to the mechanical rotor. So the limitation there is again the frequency. So you at least have to go to megahertz, because that's like the slowest frequency they can have in these, I don't know, transmon qubits or superconducting circuits. But if you can then couple this to the mechanical motion, and we have some play around with these little magnets here in levitated systems, so that's where, you know, the circle is closing, so we want to use levitated magnets, which are then like the mechanical rotors to amplify quantum vacuum fluctuations in LC circuits. Thanks.
Questions? Luca?
Thanks for the talk. When you first mentioned the expansion of the states and squeezing, you mentioned that you needed coherence on the ground state. Do you actually need coherence of the quantum coherence, sort of saying, through the whole processing of squeezing the state? How can you assure that this is going to happen?
Yeah, that's of course that's the question, yes. Okay, yes, you need it. You need basically to be faster than any decoherence effect, right? And you need to also have the operation not to be decohering your system. And what you would need to show is you would need to show that the coherence is still there after the operation, which we have not done. So that is like the big step which is missing. And that you would do again by showing a negativity in a Wigner function, or by doing some sort of interferometry overlapping different parts of this state, and then show that there is like, you know, spatial coherence in there. Yeah? That has not been shown yet. Yeah.
Yes.
Hi, thank you for the nice talk. I know you said that we shouldn't take the thermal state squeezing very seriously, like terminology-wise, but could you explain it a bit more? Like, what is the thermal state? Like, what does squeezing mean with reference to a thermal state?
Okay. So I think it's just language, and it's just what is typically used, right? So the operation as such is exactly the same. It just depends on what kind of state you apply the squeezing operation or squashing operation. If you have a minimum uncertainty state, right, a proper quantum state like a vacuum state or coherent state where the area is just, you know, h bar over 2 or something like that, yeah, and then you do this operation, then it is proper squeezing, yeah, and you also have to show that still afterwards is a minimum uncertainty state, so that the operation was not heating basically your state, yeah. Squashing is meant if you have like a thermal state, which is much, much bigger, yeah, so in phase space, so the volume or the area is much larger. But you apply the same operation, but there is like, you're not acting on a quantum state as such. I mean, I should be very careful, because there are many people who would say that also a Gaussian state is, you know, there are some quantum features in it, and there are protocols to extract it. And actually, if you look at this, there is, and Peter mentioned this, and they have done this ground state cooling, right? So that is also not like a pure state or like a minimum uncertainty state. It is also a thermal state. It is just one which is distributed over, let's say, the lowest possible states, and which it has like a really narrow distribution, but it's still a thermal state. So technically, if you apply it to any state, which people can do, I should say, in levitated optomechanics, it's not squeezing, it is always squashing. Yeah?
Right, thank you. And just one other thing, so your space experiments, I was wondering, like, when do you launch your particles?
Yes, yeah, I forgot to say it. So that will be launched in June next year. Yeah.
The particles, like, when do you, like, with your piezo launcher,
Yeah.
like, do you launch them here, or do you launch them
No,
in
that has to
space?
be in orbit. That's what we want to show, because you know, it wouldn't basically survive the rocket start
Right,
and everything.
exactly.
Yeah. So no, it basically, the rocket goes up, and then it somehow decouples, and then it goes on an orbit. It will only be on orbit for like 30 minutes. And in this 30 minutes, we want to basically, you know, activate the piezo and then launch particles and trap them in the parabola trap, and then, you know, observe them. And if we have like a successful trap, then we also want to run simple protocols like cooling or squashing, yeah, where we know how to do it. Yes.
So
Thanks.
we have a Zoom question from Andrew Garaci. Andrew, can
Andy.
speak. Andrew? Okay, we can continue with the questions here, and if Andrew is back, he can ask again.
Can you, I'm a bit slow, I think, but can you explain the amplification? I just didn't, you know, you talked about absorber, you know, an orbital angular momentum. Can you just kind of
Strange, Andy. I can hear you.
say that?
Yes, yeah, I think I understood. So you're asking how the amplification works.
Yeah.
In a way, it's very simple, classical. So you have rotational energy in your metal object, and you have, you know, also like an angular energy in the wave. And if you go in this regime, you can actually couple the two, and you transfer energy from the mechanical rotor to the wave, right? So in order to get this, you need that your matter, yeah, so the rotating object is absorbing the wave, is absorbing the electromagnetic field. Yeah, it's a metal, and then you have penetration depth, so it goes in there, it gets absorbed. But if you, and that would be like an, of course, reduction in the amplitude. So it would be in, what's the opposite? It would be a loss, right, for your wave. But if you go into the Zeldovich regime, then the loss turns into a gain. Yeah. So you have something like a negative resistance. If you draw like a circuit diagram, you get, because of this Seldovich condition, you get a negative resistance from the rotating object. That's the effect. And you know, classically we have demonstrated this, and in a way the quantum version is like super exciting, because in a way it would mean that you know, people sometimes say you can extract energy from the vacuum, right? So this would be a way to do this.
Okay, thank you.
Hi, can you hear me now, or?
Yeah.
Yeah, sorry, I think my audio had a problem. So really nice talk. I had a question about your gravity measurements. So you modulate the source mass outside the system now with some kind of bicycle wheel you were mentioning. So how fast can you modulate it, and what's your plan for modulating inside? You mentioned you're going to move the source mass inside the Kreis.
Yeah. Okay. So actually, because it's, you know, this force noise equation, the regime is, it's actually very interesting. So for gravity, it is clear that you have to be in low frequency, right? So even if you have like in high frequency optomechanical system, like a clamped system in gigahertz or so, if you put this kind of masses and frequencies into like a Newtonian gravity term, you find that you will never reach the regime to actually probe the mass of something which sits 1 centimeter distance, right? So you cannot make the mass big enough, then it would overlap with your sensor. But if you go into low frequency, so there's a 1 over omega term in your Newtonian equation, and if you have a very small frequency, then you can actually measure gravity of small masses. That's very important. So you don't want to push the frequency up. So you want to be ideally sub-hertz. So you want to be like millihertz if you can, yeah? Which is, you know, very difficult for vibration isolation. I didn't mention it here, but that's like the big engineering thing, is that you have to decouple from mechanical vibrations like crazy, yeah? So you need like LIGO technology, these gas filters, which you also have in your lab to do this sort of thing, yeah? Okay, so what we did is we picked the mode, and I think it was in the tens of hertz, and then you modulate. So there are 3 masses on the mass wheel. It's what is it? It's like an odd number, because you don't want the rotation frequency to vibrate at an harmonic of like a trap frequency, yeah? Then you don't go exactly resonance, you go close to resonance. But you know, it's on the order of 1/3 of something like 10 hertz, yeah? That is like what we did with the bicycle wheel. When for the inside the cryostat, let me maybe go to the, it's a very similar idea. Just bear with me, clicking through the slides. So there's like a, where is it? So if you can see this, so there's here still like, you know, the vibration isolation system with the, you know, the probe particle, and here is like a mass wheel which is on a long stick. And this has either, you know, mass attached to it, or holes, you know, drilled in it to reduce the mass in these spots. And again, you go for like an odd number of these. So 3 is one example. And then you spin this in a flat geometry as close as you can, you know, to this. And we think we can reach like a centimeter. The nice thing is that in these systems, because you're in a lead trap, you have this, you know, the Faraday shield for electromagnetic interaction is done by a superconductor, which, I mean, that will not be like 100% true, but on paper that should be, you know, absolutely cancel everything electromagnetic, yeah? So that is why we can go close. And then we basically spin this also. It depends on, you know, how low we get the frequencies of this guy. So you can tune the frequencies of the probe system. You can tune by shaping the trap. Yeah, you can make it, for instance, elliptic, and then how big it is compared to the size of the particle, and you can go to hertz and even to sub-hertz frequencies for the trap frequencies. So the design of the trap is the first, and then we basically match this with the speed of the mass disk. And then here we think we can, it's hard to see, but we think we can go to, in acceleration now, to 10 to the minus 13 meters per second square. So that's like the ballpark which we should reach. And that should bring us to, you know, a Planck mass, you know, sitting here on this mass wheel. So it's something like 20 micrograms or so. That's the idea. Yeah.
Thanks.
Some more questions? Well, I have a final question. Yeah. Shall we go for a beer?
Oh yes. What happened to Jason?
I don't know what happened to Jason.
Okay. So then we go for beer.
Yes. Let's thank the speakers again.